Good day, everyone. My name is Austin J. Darlo Collianto. I'm a mechanical engineering student at BIPSU or Biliran Province State University. So our topic for today is about the PVT behavior of gas mixtures, ideal gas and real gases. So, an ideal gas is defined as a gas whose molecules are spaced far apart so that the behavior of a molecule is not influenced by the presence of other molecules. A situation encountered at low densities, we also mentioned that real gases approximate this behavior closely when they are at a low pressure or high temperature. Relative to their critical point values, the PVT behavior of an ideal gas is expressed by the simple relation PV-RT, which is called the ideal gas equation of state. The PVT behavior of real gases is expressed by more complex equation of state by PVZRT, where Z is the compressibility factor. So, from this topic about the gas mixtures, it has more complex equation. It has the Z where it is the compressibility factor. When two or more ideal gases are mixed, the behavior of a molecule normally is not influenced by the presence of other similar or dissimilar molecules, and therefore, a non-reacting mixture of ideal gases also behaves as an ideal gas. Air, for example, is conveniently treated as an ideal gas in the range where nitrogen and oxygen behave as ideal gases. When a gas mixtures consist of real gases, however, the prediction of PVT behavior of mixture becomes rather involved. So, example of the PVT mixture are the air, because the nitrogen and oxygen are treated as an ideal gases. So the PVT mixture of gases has two let's say component. The first is Dalton's law of additive pressure. So what is Dalton's law of additive pressure? Dalton's law are also called Dalton's law of partial pressures, states that the total pressure exerted by a gaseous mixture is equal to the sum of the partial pressures of each individual component in a gas mixture. So this empirical law was observed by John Dalton in 1801 and is related to the ideal gas laws. Mathematically, the pressure of a mixture of gases can be defined as the summation. So these are the example of Dalton's law. So the P total or total pressure is equals to the end summation of PI. I is equals to 1, or total of pressure equals to P1 plus P2 plus Pn, where P1, P2, Pn represent the partial pressure of each component. Second is the Amagat's law of additive volumes. Amagat's law, or the law of partial volumes of 1880, describes the behavior and properties of mixture of ideal, as well as some case of non-ideal gases. Of use in chemistry and thermodynamics, Amagat's law states that the volume Vm of a gas mixture is equal to the sum of volume Vi of the key component gases if the temperature T and the pressure P remain the same. So in Dalton's law, guys, we have the pressure which is involved, while in the Amagat law are the volumes. So here's the equation of Amagat's law. Vm open parenthesis T P close parenthesis equals to K summation of Vi close parenthesis T P close parenthesis I is equals to 1. So this is the experimental expression of volume as an extensive quantity. It is named after Emil Amagat. Both Amagat's and Dalton's law predict the properties of gas mixture. So Dalton and Amagat's are the one who predict about the properties of gas mixtures. Their predictions are the same for ideal gases. However, for real or non-ideal gases, the results differ. Dalton's law of partial pressure assumes that the gases in the mixtures are non-interacting with each other, and each gas independently applies its own pressure, while the sum of which of the total pressure. Amagat's law assumes that the volume of each component's gas, same temperature and same pressure, are additive. The interaction of the different gases are the same as average interaction of the components. So in Dalton's law, guys, it applies its own pressure, while in Amagat's law, it has the volume that assume of each component. It has same temperature and same pressure. Heat capacity. The heat capacity at constant volume of an ideal gas is CV equals this one. Don't know how to read this. Next, it is seen that the constant is just the dimensionless heat capacity at constant volume. It is equal to half the number of degree of freedom per particle. For moderate temperatures, the constant for a monoatomic gas is CV is equals to 3 halves, while for a diatomic gas is CV is equals to 5 halves. If it is seen that macroscopic measurement on heat capacity provide information on the microscopic structure of molecules. So this one Cp is equals to this, or equals to Cv plus 1 N times K, where H is equals to U plus PV is the enthalpy of the gas. It is seen that also constant and that the dimensionless capacities are related by Cp minus Cv is equals to 1. So PVT behavior of gas mixtures, ideal and real gases. The prediction of PVT behavior of gas mixture is usually based on two models, the Dalton law of additive pressure and the Amagat's law of additive volumes. So Dalton's law of additive pressure. The pressure of a gas mixture is equal to the sum of the pressure of a gas would exert if it existed alone at the mixture temperature and volume. So in the Dalton's law, guys, gas A plus gas B, which contain the volume and temperature, the gas mixture are pressure A plus pressure B. While the Amagat's law of additive volume, the volume of a gas mixture is equal to the sum of the volume each gas would occupy if existed alone at the mixture temperature and pressure. So, in Amagat's law of additive volume, gas A, pressure and temperature, plus the gas B, pressure and temperature, its volume is the sum of each gas, which is volume A, gas A, plus volume gas B. The Amagat's law of additive volumes for a mixture of two ideal gases, while the Dalton's law of additive pressure for a mixture of two ideal gases. And that's all. Thank you. Bye.